The next collision resolution strategy is linear probing. Now with linear probing, we hash a data item to a bucket as usual, and if the bucket is busy, we start to linearly search from that point through the table until we find an empty spot to insert the data item. So let's see how that works with our example hash function h of x equal x mod size, which is 10 in this case. And let's do a sequence of insertions. Let's insert first 25. So h of 25 is 5. So we go to bucket number 5 and insert 25 right here because it's empty already. Now let's do 16. H of 16 is 16 mod 10, that is 6. So we hit bucket number 16 and insert it, bucket number 6 rather, and insert 16 right there because it's empty. Now let's do 35. H of 35 is again 5. So we hit bucket number 5. Now bucket number 5 is busy, so we check bucket number 6. Again busy, we check bucket number 7. Now bucket number 7 is empty, so we can insert 35 right here. Now if we need to search and we couldn't find a spot and hit the end of the table, we can wrap around and continue to search until from the beginning of the table until we find the spot. But in this case, we found a spot right here, so we'll insert it right here. Now let's see how search would work with this insertion scheme. So let's do search. So let's search for 25. So again, we need to compute h of 25, which is 5. 25 mod 10 is 5. We hit bucket number 5. Now bucket number 5 has the value 25, so we declare it found. Now let's search for 35. H of 35 is again 5. So we hit bucket number 5. Bucket number 5 doesn't have the value 35, so we linearly search. Check bucket number 6, 35 is not here. Check bucket number 7, 35 is here, so we declare it found. Let's see how we can search for, let's say, 26. H of 26 is 26 mod 10, which is 6. So we hit bucket number 6. 26 doesn't exist here. So we start searching linearly. So check bucket number 7. 26 is not here. Check bucket number 8. Now we hit an empty bucket, so we can confidently declare it not found, because if it was actually in the table, it would have been inserted here. So once we hit an empty bucket, we declare the data item not found. Now there's a little problem with this scheme. So what happens if we do some deletions after insertion? So let's say we deleted 16, and now we want to search for 35. So 35 mod 10, that's 5. So we hit again bucket number 5. 35 is not here, so we linearly search. Now this is an empty bucket, so we're going to be declaring 35 as not found, even though it's actually available in the table. So to overcome this problem, what we can do is that we can mark deleted buckets differently from empty buckets. And while searching, we don't stop at a deleted bucket. We only stop at an empty bucket. So in this case, if we're searching for 35, 35 mod 10, that's 5. We start from bucket number 5. 35 doesn't exist. Check bucket number 6. That's a deleted bucket, so we don't stop. Check bucket number 7. It exists now, so we found it here, so we declare it found. Now, in terms of performance, let's check the performance of these operations. Now, when we insert, in the worst case, it could be that the table is full, which would, we will need to start at a bucket. Let's say we're doing 25. We'd start at bucket 5, and then we will check every spot in the table until we can figure out that we cannot actually insert the data item, so that's a failure. Or insert the data item, just right here after checking all the spots in the table to find an empty spot, let's say here. So that's in the worst case is basically an order of n operation. Search is just the same. I might need to check every item in the table before declaring a data item found or not found. So that's another order of n in the worst case. Now, again, hopefully with proper sizing of the table, we can ensure that this worst case doesn't happen quite often.